Hello and welcome. In this workshop, we will demonstrate how to use the Ansys Fluent Meshing Watertight geometry workflow to generate a simulation-ready mesh that can be used to perform the conjugate heat transfer analysis of the battery module. Specifically, we will focus on creating linear mesh patterns of a battery unit to create a battery module and also demonstrate how to perform shear topology to facilitate the generation of conformal polyhedra mesh. Let's get started. Launch Ansys Fluent in meshing mode. For this demonstration, double precision is enabled and 4 processes are engaged for meshing. Once Fluent meshing launches, select Watertight geometry workflow. In the import geometry task, leave all the settings to default and load the provided geometry file. The model we have here is that of a battery unit which consists of 2 cells separated by a rectangular cooling fin with a foam spacer on one side of the unit. The opposite terminals of the cells are connected with the help of the connectors, as can be seen here. Let's start with the workflow. We will not be adding any local sizing. Next, in the Generate the Surface Mesh task, set minimum size to 0.5 mm and maximum size to 5 mm. As the parts are thin, to ensure the presence of an appropriate number of cells in the gaps between the geometrical features, set the cells per gap to 2. Click on Generate the Surface Mesh. Once the surface mesh has been generated, right-click on the Generate the Surface Mesh task to access its task-specific context menu and select Add Linear Mesh Pattern task from the Insert New Task menu. Note that it is important to add the task here before executing the Describe Geometry task. In the Add Linear Mesh Pattern task, you first need to choose the part that you would like to pattern. Go ahead and pick all the parts as we have to create patterns of the complete battery unit. Next, you have the option to let Ansys Fluent automatically estimate the axis and pitch for the pattern. The default setting is pitch only. We will change this option to no to avoid any automatic estimation. Next, for the axis direction, we want the battery unit to be patterned in the negative x direction, and hence we will specify the x component as -1 and set y and z components to 0. Now we need to specify the pitch or displacement factor that defines the spacing between the components of the pattern, which is 24 mm in this case. This value is very critical and can be determined at the CAD level. Incorrect value will result in misalignment of the patterned parts and will lead to failure while performing shear topology. In the total number of units, enter 10, as we need a total of 10 battery units including the original unit in the module. You can now preview the pattern by clicking the Preview Pattern button. Change the Highlight Unit Alignment option to Yes to highlight the interfaces between the pattern units or the pattern and any other geometry it is attached to. The highlights are visible once the task is executed. Once you are satisfied with the inputs, hit the Add Linear Mesh Pattern button. Ansys Fluent will now make linear patterns of the selected parts based on these inputs. Notice how the intersection between the parts are highlighted. In the Describe Geometry task, set geometry type to the geometry contains only solid regions. We will not be extracting any fluid regions, and also there is no need to create internal fluid boundaries as there are no fluid regions in the model. Make sure that Do you need to apply shear topology is set to yes. Shear topology operation will not only ensure the connection of parts within a battery unit, but also between the patterned battery units. Once you execute this task, you will be taken to the Apply Shear Topology task. The max gap distance and the shear topology method can be left unchanged. Click the Apply Shear Topology button. Once this is done, the linear mesh pattern is fully created and the geometry overlaps have been successfully handled. Next, in the Create Regions task, keep the number of estimated fluid regions to 0 and move to the Update Regions task. In this task, make sure that all the regions are assigned with solid region type and execute the task. Next is the Add Boundary Layers task. Boundary layer mesh can be considered in the solids for better prediction of temperature gradients on the interfaces, but for this workshop, we won't be adding any boundary layers. Click on Update to move to the Generate the Volume Mesh task. In this workshop, we will use the polyhedra fill width method, which is the default, to generate a conformal poly mesh throughout the battery module. Leave all the inputs to their default settings. Make sure that the Mesh Solid Regions option is ticked before executing the task. Hit the Generate the Volume Mesh button to create the volume mesh. The generated mesh has a total of approximately 1.9 million cells with a mesh quality of 0.2. Hence, we have generated a good quality conformal poly mesh, as can be seen from this sectional image, which can be used for performing conjugate heat transfer analysis of the battery module. That brings us to the end of this workshop.